My name's Sasha Kylo. I'm the co-chair of the Alarm Industry Communications Committee, part of the Monitoring Association. I'm happy to be here. Thanks, Jake.
Taylor?
Good afternoon, everyone. My name is Taylor Criddle. I serve as the Vice President of Advocacy and Public Affairs for the Electronic Security Association.
Michael?
Hi, my name is Michael McGinley. I'm the Senior Systems Engineer at Pericle Communications and RF Consulting Company.
Thank you. So the reason why we're here is that we're going to be discussing an important report that Michael is formulating. He'll be presenting the results of. But April of last year, a company filed a petition with the Federal Communications Commission that would radically change the FCC's rules governing what's known as the lower 900 megahertz frequency band from 902 to 928 megahertz. This proposal would give the petitioner, NextNav, 15 of the 28 megahertz to provide a high-power 5G system for location services and would remove the protections for the unlicensed devices that operate in the lower 900 band against harmful interference. So this petition immediately garnered a lot of concern from the different industry sectors that utilize this band. And security being a significant one. We joined hundreds of other associations and companies in raising concerns about this. But we wanted to go a little bit deeper and make sure that we really understand and communicate what the full impact of this would be. And so the Security Industry Association, with the support of ESA and the TMA, commissioned this independent analysis from Pericle Communications Company that would actually go deeper and examine the impact. And so Michael's going to present the results of that report, but in the meantime, if you have any questions, please use the Q&A box in Zoom and put those questions in written form, which we will get to either throughout the presentation or more likely at the end, where we'll discuss a few more things as far as key questions that have come up, but also next steps that the organizations contemplate. So with that, Michael, I will hand it over to you.
All right, everyone. Just to refresh it again, I'm Michael McGinley. I'm a Senior Systems Engineer here at Pericle Communications. We're an RF consulting firm, just moved out of Colorado Springs into South Denver. And we were retained by the Security Industry Association and some other associations to look at the coexistence to do a coexistence study between NextNav's proposed 5G network and the incumbent or the unlicensed devices that already occupy the spectrum. And just a little background on us, we're a pretty old consulting company, but what's relevant here is what we're looking at is two disparate network types sharing the same spectrum. In the case of NextNav, it's a 5G network, 5G essentially cellular network, occupying the same spectrum as these narrowband. A majority of them are narrowband hopping devices. Some of our relevant experience in this area is, if you remember Nextel, the push-to-talk people, they used to be Sprint and interleaved with public safety in the 800 megahertz. We were a major contributor to the FCC's effort to separate the bands. So Nextel got their own contiguous chunk and public safety got their own contiguous chunk. Essentially, public safety got 806 to 816 megahertz and Sprint Nextel got 817 to 824 megahertz. In addition to that, I was a major contributor to Anterix or PDV, Pacific Data Vision's efforts to move the 900 megahertz narrowband channels from just continuous 12.5 kilohertz or 15 kilohertz channels for voice radio to a broadband channel. That effort was successful. That broadband channel's now used by quite a few utilities across the country for data, essentially. And that's very similar to this. So what I had to prove in that study was that having a broadband LTE channel adjacent to your land mobile radio or your push to talk radio, your two-way radio, wouldn't cause any more interference than the existing channels were there. In addition to that, I personally have about 15 years of experience looking at interference to LTE sites. Coming out of school, I was part of AT&T's Tiger team looking at interference to cell sites and determine the impact of interference. We've done the same thing with land mobile radio. So any of your public safety communications. And then in addition to that, we were a major contributor to the TIAs, the Telecommunication Industry Association's strong signal interference thresholds and procedure. And essentially what that is that's just if you have a really strong signal adjacent to your channel, how is that going to impact the device the victim receiver in the adjacent channel? And that's quite relevant here in this study because the 5G channel that NextNav is asking for would be putting out roughly 4,000 watts across the channel. Whereas if you look at the incumbent device, the max that the incumbent devices or the Part 15 devices right now can put out is 2.5 watts. So 4,000 versus 2.5 is a pretty large delta. So here's just a quick overview of the current Part 15 900 megahertz environment. It's 26 megahertz of spectrum. This spectrum is used by everything and everyone. So you have motion sensors, you have carbon monoxide detectors, you have smoke detectors, security cameras, flood sensors, door sensors, window brake sensors. Essentially, any device that needs a low amount of throughput or needs to put out a low amount of data and doesn't have to do it very often, or very far, this is the ideal spectrum for them because you don't have to license FCC spectrum to put your device there, and that's why they call it unlicensed spectrum. You just have to play by the rules of the spectrum already and get your device certified to use in that spectrum. So these rules currently, a majority of the devices are frequency hopping spread spectrum. The spread spectrum there is a bit of a misnomer. They're mostly just frequency hopping, and they call that spread spectrum. And essentially what that means is depending on the power output and the bandwidth of your channel, the FCC tells you how many channels you have to hop between and how long you can stay on that channel. And that gives a very ephemeral effect to interference between users out there. If your device is randomly choosing one of 50 channels in that spectrum, odds are that they're going to find a channel without interference in a very short period of time or no time at all. The first channel they find could be interference free and they can transmit, and that transmission can go through. Right now, those devices are limited by the power that they can transmit. This is part of the FCC's goal or previous goal with the spectrum is if you limit the power, it makes the environment a lot easier to coexist in. The power is limited to 1 watt with a 6 dBi gain antenna. If you do the math, that comes out to 2.5 watts when you incorporate the gain of the antenna. It is important to note that a lot of the devices that I listed before are battery operated devices. A battery operated device that transmits at full power isn't going to have a battery for long. So a majority of these devices that are battery operated, they're operating in the 100 to 200 milliwatts. So a tenth to a fifth of a watt of power. Right now, the unlicensed devices must accept interference from licensees. There are licensees of this spectrum. There's only one licensee left now. The spectrum, the licensed owners of this spectrum or holders of this spectrum previously were multilateration location services and monitoring services. These were actually developed a little before my time in the 1990s, and the goal of the multilateration location services was to use this spectrum to build a network that gives location services on fleet vehicles, essentially. And then the monitoring services were similar to toll services right now. Essentially, you drive through a reader or past a reader, and it provides data on your vehicle as you drive past. NextNav now has bought up all the previous licenses because every company that tried to do this went belly up, and NextNav was able to acquire their spectrum when they went into bankruptcy. NextNav does claim to have built a multilateration network in San Francisco, and they cite this in their technical study that went on the air in 2012 and consisted of 34 sites. They from what I've seen online and in press releases, they haven't stated that there were a single user of this service, of this multilateration service. I would assume because of cell phones and GPS, but they do claim that they were using the spectrum, and that's a big part of the FCC is you have to use it or you lose it. So here's just an example of Part 15 devices in personal homes right now. We touched on a lot of these. Key fobs are another large part of this spectrum. Just the RFID key fob that you use, or this is actually for garage door, but the RFID card that you use to get into your office. And all these devices will typically talk back to a keypad or a hub. Another large one that that we were looking at was panic buttons. There's personal or consumer use as well as commercial use of panic buttons that specifically use this spectrum to communicate an emergency from the panic button. You've got cameras as well as doorbells, smoke detectors. The smoke detectors also have quite a few industrial uses where if you have a room that's shut in and isn't regularly monitored, a smoke detector can't typically be heard in there, and you can get a wireless connection to it that tells you if there's been smoke detected in that room. So here's just a look at what the proposed environment is versus the current environment. If we look at this top bar, that's the current plan. The A and the C block are for multilateration services. Those are the vehicle location services, and LMS was for just reading vehicles. And then if we go down one more bar, we can see that NextNav has now bought up. The FCC took part of that A, but the NextNav has acquired all the other blocks in the spectrum. So essentially, of this band of spectrum, they are the largest spectrum holder. And then if we go down to the last bar, we can see what NextNav is proposing. It's a 5 megahertz uplink at the bottom of the band with a 10 megahertz uplink at the top of the band. So we would be going from 26 megahertz of spectrum. We subtract 15 from that, and we get 11 left. And so all the devices, we'll see this later in the presentation, but all the devices would be essentially forced to live in this spectrum because they would continually detect interference on the 5G channel and move off of it. So here's just a basic overview. So the 5 megahertz uplink is going to be the phone or whatever the wireless device is. That's the channel that it uses to talk back to the cell site. The 10 megahertz downlink is the cell site to phone. Oh, that should be S. Cell site to phone. We went over this already, but their proposed downlink would transmit at around 4,000 watts. Current devices are limited to 2.5 watts, so a massive power discrepancy. And like it says here, the power difference will result in a pretty large reduction in the range of current Part 15 devices. So one thing we have to consider when looking at any sort of channel like this is not only the energy in the channel, so that 4,000 watts is the 4,000 watts, if you can see my screen, is located in this rectangle channel between T1 and T2. But there's also a good deal of energy that comes out of the skirts of the channel. So even if a Part 15 device didn't happen to fall within their channel, there's a large amount of energy outside of the channel, because no radio is perfect and no amplifier is perfect. And by that, I mean no radio or amplifier is going to amplify all the energy just within your channel. There's always going to be out of band emissions. Those out of band emissions are regulated by the FCC, but they are a function of power. And it comes down to a formula, 43 plus 10 log P, P being the power of the channel. So one thing that NextNav doesn't consider in their study at all is they look at interference to Part 15 devices, and a large part of their argument is saying, hey, we're a 5G channel, this 10 megahertz 5G downlink and a 5 megahertz uplink is actually better for Part 15 devices than the LMN, the multilateration services. And that was the crux of their argument, that we're already licensed for this spectrum. We should start using it for a GPS backup. And here is why giving us a 5G channel is better than the current rules. And they neglect to say that they've only deployed one of these networks in downtown San Francisco, and it consisted of a paltry 34 sites. So what NextNav doesn't look at or even consider in their study is that while they will cause interference to the existing Part 15 devices, the Part 15 devices are going to cause so much interference to NextNav that it will almost render the network unusable. Back when I would help AT&T with interference at new sites, if we had a single spur in our spectrum, we would hunt it down pretty vigorously, and we would use the FCC Enforcement Bureau if we had to get the offending device or bidirectional amplifier turned off. That's simply not possible in this spectrum. A number that NextNav cited that the Wi-Fi Alliance used, and they're a contributor against NextNav, is that there are billions of devices in the US in this spectrum. That's just simply too much interference for any type of 5G network to tolerate. 5G networks are built to operate in very clean spectrum, and they can't tolerate interference at all. And the major problem of interference is your smoke detector, your carbon monoxide sensor, your RFID isn't always going to be transmitting and causing interference. Well, an RFID would be, but the others wouldn't. But what they have is a heartbeat or a check-in signal. And this is just a signal that it ranges from roughly 256 seconds to 3 minutes or 3 hours, depending on the devices. But it's just a check-in by the device to its hub saying, I'm working. Maybe here's my battery status and a few other status updates to the hub. And these transmissions would just be a constant source of interference to NextNav. And if you take some of the numbers that the Wi-Fi Alliance cites and you intersect that with, so what I did was they cited 4 billion. I took a very conservative 10% of that 4 billion, so 400 million. I saw how many devices per household based on census data, and did the math, and you get roughly 50 occurrences of interference to a single NextNav cell site just within their downlink, that not even uplink interference. And anytime interference happens to a cell site like a 5G or a 4G cell site, it lowers the amount of resources. So you would see the throughput of the cell site go down, and you would, if you say you were traveling between cell sites and there was interference as you were trying to hand off to the next cell site, the closer one, you would see your call get dropped or other problems like that. So what we did was we did very similar modeling to what NextNav did, and it's sort of become the norm with these types of petitions to the FCC. You do two types of modeling. So the first type that we did was wide area coverage modeling, and basically what that is doing, it's just using a computer aided propagation tool. You build what's called a notional network, so just a network that could potentially be deployed, but it's not a really well thought out network. And then you put that in a location. In our case, we used just right by Dulles Airport. It's the same location that NextNav used, and we did that on purpose to show the delta in our two models. And then in addition to that, you do Monte Carlo simulations. And what a Monte Carlo simulation is you build in a set of parameters, but a lot of those parameters you give a range of values to, such as distance between a transmitter and a receiver, transmitting power, the ability to frequency hop, and you run hundreds of thousands, in our case, 200,000 of these simulations, and you get a probability of interference to a victim receiver. And so the focus of my modeling was to bound the problem. That's what you always want to do. In NextNav's study, they take the lower bound of every single value that they can, which makes sense. You know, if you're doing this this work from their end, you want to present the best looking information for your side. I tried to stay well within reasonable bounds. But I did take, so for example, in the Monte Carlos, and we'll go over this later, I did put the devices far enough away that they're close to the edge of their network, but they're still well within their range. And the reason I did this was because I wanted to show the effect of what devices close to the edge would look like. Whereas in NextNav's case, they assume the devices are quite close together, which obviously is going to give you a much better picture. So here's just a quick overview of the types of devices that we looked at and why we looked at them. So 200 kilohertz, and this is the bandwidth, or in this case, it's the blocking bandwidth. But a 200 kilohertz device, it's a narrow band signal, represents the low throughput devices such as panic buttons, motion sensors. A majority of the devices that we talked about earlier. 500 kilohertz represents what we're referring to as a medium throughput device. This could be a wireless microphone. I've personally found wireless microphones interfering with cell sites before. License-free two-way radios. So there are two-way radios that exist inside of this spectrum that first responders do use. And they're cheap radios that you can get. Say you're a volunteer agency and you don't want to put out the money to get a Motorola or a Harris radio. You can get much cheaper unlicensed radios in the spectrum. And then 2 megahertz is representing the high throughput devices. And really what The high throughput devices are obviously doorbell cameras, but there's also ISPs or WISPs, wireless internet service providers. So in rural areas, WISPs will use this 8 megahertz to provide backhaul, and all backhaul is a connection, a wireless connection to where they have a landline. So it would really impact the 8 megahertz WISPs. As you increase in your bandwidth, you allow in more of NextNav's energy. So the front end of your radio lets in more energy, so you're more susceptible to the interference. So a lot of, you'll see this later, but a lot of the focus is on the 200 kilohertz devices, because one, they're the most resilient to interference. So you can make the logical leap that if your 200 kilohertz device is having a hard time functioning in this environment, your 500 and your 2 megahertz and your 8 megahertz will have a much harder time. And the 200 kilohertz also reflects a lot of life safety devices. So here's a piece of the map that we submitted to the FCC. So what I did here was I built a notional network similar to what NextNav had done in their own study. The sites, and this is just looking at coverage outdoors, bear in mind. And that's the reason that we focus on outdoors with the wide area modeling, is because one, a majority, not a majority, but a good amount of these devices exist outside. RFID building entry with RFID, wireless microphones for first responders, um, the cameras, WISPs, what have you. There's quite a bit out there. And so I built a network here that would serve as a 5G network for NextNav. And one thing to consider in this, and I don't think we've touched on this yet, is that what NextNav is proposing is that they are going to be a backup to GPS. And the way that they do this is baked into the latest 5G standards, the 3GP 5G standards, is a new location sharing functionality, I guess I would call it. And what it does is you triangulate your location from three, technically four, but three cell sites hitting you. And what that does is when you're building a cellular network like this, or Verizon or AT&T, you typically don't want a lot of site overlap between your two sites. And the reason for that is because you get an effect called intercell interference. Essentially, your two sites are having to talk over each other in a loud room. And each site that you have, each time you have one more site covering that room, the ambient noise in the room just gets louder. And so a lot, you wonder why the cellular carriers, AT&T, Verizon, T-Mobile, haven't come out and said that we can already do this. Why go to NextNav? And in my opinion, it's because the density of sites is just, it's going to be far greater than what NextNav assumes in their technical study. If you do go and read their technical study, you'll notice that they don't put any site locations in their maps. And I think that's to deliberately obscure that in their study, they grossly underestimate the number of sites that they need for multilateration location services, or PNT. And the reason for that is they just built a network that's your traditional 5G network, where there's not a large amount of overlap between two cell sites. So this is, with all that in mind, this is the amount of energy within the downlink. And you can see that a majority of it, and I think I've got a histogram out after this. This is a histogram of all that data. So this is a statistical breakdown of how many points were at each signal strength. And you can see that the mean or the average value is right around minus 67 dBm. So just to give you an idea, without NextNav present, this minus 67 dBm would be, roughly minus 120. I think it's minus 122.8. I think that's why I used that number. Would be minus 122.8. One thing you have to keep in mind is that these are logarithmic units, not linear units. So that's for every 10 dB difference, it's a 10x in the linear world. So there's just essentially what this map shows is that 10 megahertz of their downlink, and they assuming it's fully utilized, would be useless for any Part 15 device operating in an outdoor environment. So here's a little just a few blurbs on that. So in an interference-free environment, the typical sensitivity of one of these radios is minus 105 dBm. In this scenario shown above, and I think I did a 10 by 10 area for this 10 miles by 10 miles for this study and took the statistical data from it. We would see the sensitivity reduced to 68 dBm. So if we say that's 35 dBm of difference, we get 10 times 10, 100 times 10, 1,000, and then times essentially doubled. That's a 2,000. Your signal would need to be 2,000 times stronger. So if originally you had a 1 watt signal coming from your device, you would then need to be a 2,000 watt signal to overcome the best case scenario of this sensitivity. And this minus 68 is actually based on the lowest number recorded here in my study. So just a few statistics from the histogram of the in-channel power of NextNav outdoor. And you can see that as the bandwidth increases, so as you take in more energy, your in-band channel power increases quite a bit. And the maximum numbers reflect intuitively, you probably know this, reflect the area right around the cell site. And these maximum numbers essentially mean that if you're close to that cell site, your device is going to have a really hard time if it's inside of the NextNav downlink. And then the mean channel powers just show that there's a substantial amount of energy inside of that downlink, and that's because they're asking for the same rules that govern the same power rules that govern the 800 megahertz channels. So the Monte Carlo simulations. One thing that the outdoor modeling doesn't take into account is adjacent channel interference. If you remember back, not only do we have energy in channel, but we have the skirts of the channel. We have the out of band energy, as it's referred to. So these Monte Carlo simulations, for them, I use the out of band emissions defined by 3GPP, the standards body for 4G and 5G. I could have used the FCC out of band emissions limits, but 3GPP is a little bit stricter. So it's typically best to use them, and all these radios have to be 3GPP certified. Monte Carlo simulation also takes into account receiver blocking. Receiver blocking is any time that there is a large amount of energy coming in the front end of your radio. So right now, all these Part 15 devices will pass anything from 902 to 928 megahertz. They're not designed to coexist with these with the 5G channel. So they'll pass that whole chunk of spectrum. But even if, but if you allow in a 4,000 watt channel into the front end of your radio, it can cause severe degradation. There's a lot of different ways that can happen. An amplifier going non-linear, an analog to digital converter, uh, essentially going non-linear, or its front end is getting overloaded. But there's a lot of different ways, and that's what's called receiver blocking. And the receiver blocking metrics that I used were based on proprietary numbers given to me by SIA members. Like I had said before, the simulation is built to have. When I built the simulation, I put the victim devices, so the Part 15 devices, far enough away that they were well within their coverage area, but at the same time they were getting close to the edge of their coverage area. Use an indoor path loss model. Path loss model is just how much the signal is attenuated between the transmitter and the receiver. Victim receivers were built using member supplied data, and then the 3GPP emission mask was applied to the next nav channel. One thing to consider is we didn't look at the uplink, and that's simply because it's hard to nail down. There's a lot of variables to consider, and uplink usage and utilization is very very variable. So here's a look at what the output of one of these Monte Carlo simulations is. If you're wondering why this is 200 kilohertz up here, 130 kilohertz is the bandwidth of the channel, while 200 kilohertz is the blocking mask of this device. And so if you look at all these dots, this is a visual representation of the 200,000 simulations that were run. At the very center of this, you have a green dot. That's the victim link transmitter. So that would be the hub in the house, the hub in the industrial park, the hub in your office that everything talks back to. The blue devices are the receiver that are trying to receive from that hub. And if we were to look at one of these scenarios, what you would end up with is you'd end up with one red dot, which would be a NextNav 5G channel, one blue dot, and then the green dot. And what this simulation is doing is it's each new simulation, it's randomly, and I'll go over these a little further later, it's randomly picking a location. I think I used a half kilometer for this one. It's randomly picking a location for NextNav within this half kilometer radius and putting them there. And it's also randomly picking a Gaussian distribution of power for the NextNav site. Then it's randomly, and there's also some other variables in there, but then it's picking a random location for the receiver within this defined radius. I think I used 100 meters, might have been 130 meters for the receiver. It's in that receiver, it's randomly picking variables such as loss through walls and the channel that the receiver's on. So because these are frequency hoppers, I'm able to build that into the model. So each one of these simulations, the victim receiver is hopping to a pseudo random channel and trying to use that channel. And the three things that we get out of this simulation are what's called a DRSS, that's desired received signal strength. You can see that this is at roughly, the green line, that's the mean, is at roughly minus 90. If you'll remember, the sensitivity of this device is minus 105, putting us roughly 15 dBm above the sensitivity. So in linear terms, that would be roughly, we're at 20 times the power that we need to be, maybe 30 times the power that we need to be to receive the signal. So we're well within our parameters for receiving. And I do throw out any values that are below the receive signal, the sensitivity of the device. Then we have IRSS, that's unwanted interference. And what unwanted interference is, any co-channel interference. And one thing you have to remember is co-channel just means energy in your channel. So this takes into account not only when the Part 15 device is on the same channel as NextNav, but also when NextNav's out-of-band emissions, which are ruled by the 3GPP emission mask, when their emissions are on the channel. And you can see that the unwanted is, I think I do statistics later, but it's roughly minus 92 dBm. And then if we take into account blocking, and blocking is the ability of the receiver to ignore a strong signal in its band. If we take that into account, we're up to minus 85 dBm of mean interference values. So the second output of this, and this is a frequent thing that the FCC likes to see, are these CDFs. A CDF is a cumulative distribution function. And basically we can derive or find our probability of interference by looking at this line here. The vertical line is our minimum C to I, our minimum the amount of signal above the noise that we need to see for that device to work. I think in this case it was 12.5 dB, I want to say. So if we look at where that line intersects this distribution function, and we just go over here, we see in this specific scenario, there's roughly a 60% chance of interference. So what that translates to the device is, it's going 60% of the time that it transmits, it's not going to be successfully received, and it's going to have to hop and hop and hop until it finds a channel far enough away from NextNav, or maybe while NextNav's not transmitting close to it, to push that data through. If we look at that same environment and we take into account blocking, so strong signal interference into the front end of the receiver, we see that probability of interference roughly increases to 85%, meaning that 85% of the time the device transmits, it's not going to be received in this specific scenario. So if we go and we look at the statistics from the Monte Carlo simulations, left side here is the coverage radius of a NextNav site. I think in their notional network, they've got an inner cell difference, or inner cell distance of 1,300 meters. So that would be somewhere in between 1.5 and 1 kilometer. Narrowband device. And this is just the probability of interference. This does not include blocking. That's a good thing to remember. In my opinion, NextNav should have released a study in conjunction with their technical study, doing a lab environment study showing how resistant to blocking these radios are, but we haven't seen anything like that. So 900 megahertz, and you can assume intuitively, as you get a smaller coverage radius, or we put the victim device closer to NextNav, we see a large increase in that probability of interference, not including blocking. So yeah, up to 60% when you're within a half kilometer. So it doesn't necessarily mean that these devices aren't going to work in that half kilometer. It just means that they're going to have to transmit quite a few more times before they work. And if we were to reduce this to even closer, we could potentially see the device going non-functional. Okay, if we take into account blocking, as well as interference. Obviously, we get a bigger number because not only are we just looking at interference energy, we're looking at the front end of that radio getting overwhelmed. Within a half kilometer, you can mostly scratch the 802.11ah. That's the Wi-Fi standard for the 900 megahertz. And the reason for that is Wi-Fi chipsets aren't great at handling strong interference. If you think about Wi-Fi, it's low power and it's only having to deal with other low power devices, and that's a big argument against NextNav is that these these are two disparate technologies. They couldn't be more different, and they're supposed to occupy the same spectrum. But if we look at the narrowband channel, we're at an 85% probability of interference and blocking within a half kilometer. That's pretty darn high. It I'm not sure if I would say that it renders it unusable, but it's getting close. So here we touch on a few issues that Pericle that we at Pericle had with the NextNav study. So a big part they did release a press release targeting this. What the 5G 3GPP release says is that essentially, as these three or four sites are talking to your phone to give it position data, to send it position data, they're called PRS signals, and you look at the time of arrival of the signal. But each site will mute themselves. So each site in your area will mute themselves on that frame, so it doesn't cause interference to itself. And while that's well and good, and there's white papers written by LTE and 5G manufacturers to this effect that it does work. They still don't address the intercell interference issue, and that's the interference the cell sites cause to each other. It leads to a really poor cell design and an inefficient use of the spectrum, because as you have these cell sites talking over to each other, there's more interference, there's less throughput of the cell site. With my large amount of experience with the cellular carriers, just mostly the big three, none of them would accept the amount of interference in this spectrum. They simply wouldn't touch this spectrum with a 10-foot pole. These devices are going to be living in this spectrum for, I think, at least the next 10 to 20 years, even if the FCC were to rule in NextNav's favor. And there's simply way too many of these devices for NextNav to be going door to door and hunting them down. It would just take way too much time. That brings up another thing that I don't think we mention in these slides is previously with multilateration services, there was a safe harbor agreement in the FCC rules, meaning that a multilateration service would have to show that they can peacefully coexist with the unlicensed Part 15 devices. In the case of San Francisco, I think NextNav had to do some lab testing, and then they had to set up a website for people to complain, and naturally no one complained. But that is the case with these things. People don't know what they don't know. And so their proposal, the NextNav petition, would do away with these safe harbor rules, meaning that they could come after unlicensed devices that were causing interference to their sites. Another flaw in their reasoning, and I think part of the 5G standard, but I think NextNav stretched what it was supposed to be used for, is that any building, if you're in a large auditorium or a convention center, they're going to have a DAS, a distributed antenna system, essentially meaning that you'll only have a single cell site covering your whole area. and any positioning, you're not going to have 3 sites, you'll have a single site. So your location will always be limited to that, just to the building. So it sort of does away with their whole proposal. And then I think the biggest argument, and this is what should sink NextNav's ship, is that they're just wildly disparate technologies. One is low power, short range, frequency hopper, and the other is a wide area broadband channel. And what this means is if we look back to the Sprint Nextel days and the push to talk, and public safety. So in those days, it would be a public safety channel, then a Sprint Nextel channel, and they just did every other the whole way. But because Sprint Nextel had to build a good deal more sites than public safety did because they're transmitting on a ton of channels, whereas public, so think about how many cell sites you see, and then for a city, take Denver as an example. The city of Denver has 5 transmitter sites versus Sprint Nextel probably having 3 to 500 in the city. Because of those wildly disparate network topologies, they caused interference to each other. And it wasn't public safety to Sprint Nextel. It was Sprint Nextel causing interference to public safety, and that's why the two spectrums got broken up. And simply, to put it as simply as I can, they cannot coexist in the spectrum. What NextNav is proposing is going to take those 15 megahertz and it's going to make it unusable to anybody. Essentially, their cell sites are going to keep trying to transmit, and they're going to try and overpower the 900 megahertz part 15 users. Those part 15 users are going to say, hey, you know, I lost my connection to my carbon monoxide detector. They're going to put in a new hub that's going to be transmitting all the time, causing more interference to NextNav. And it's just going to create a positive feedback loop within the spectrum that's going to hurt not only NextNav, but it's going to hurt the part 15 devices that already use the spectrum quite harmoniously. Yeah, and we spoke to this with the FCC that no previous rebanding has asked people to share spectrum with each other. It's always there has to be a delineated type use for each piece of spectrum. It's going to destroy the spectrum for everyone. And that's all I had.